to 20, which are about the core and the memory hierarchy. Each lab is divided in two parts. There's first a theoretical explanation of the concepts, and then the illustration of the concepts using mainly a very later simulation of an example program. We also provide exercises to deepen understanding of the described concepts. So Lab 11 is an introductory lab which explains the SweRV EH1 organization, configuration, and also how to use performance monitoring available in the processor. We include this diagram which includes the different modules available in the system on chip, in the processor. So we have two main blocks, one for memory-related modules, one for core-related modules, and then there are subgroups, one for the fetch unit, for example, which includes the instruction catch control, or the align module, or the branch predictor. One for decoding, which includes the register file, the decode control. One for execution, which includes the different execution, the functional units that we have available here, which is an arithmetic logic unit, a multiplier, and a divider, and so forth. As for memory, we have the iCatch and two software-controlled memories, one for instructions, one for data. So this is useful in case you want to inspect the modules for the SoC. This is the figure provided by Western Digital for SweRV EH1. SweRV EH1 is a 32-bit, two-way superscalar 9-stage pipeline in-order processor. It's an in-order processor. So this is a high-level diagram. And in this lab, we include more detailed figures for the core. We divide them in two parts. First figure for the three initial stages, the two fetch stages and the align stage, and then one figure for the remaining 6 stages from the decode stage to the write back stage. So, well, let me describe a bit these figures. So in the fetch stage, the fetch address is provided to the memory controller, which accesses the instruction catch and the instruction scratchpad memory, the software controlled memory for instructions. But in this case, this is shadowed because this is disabled in our original implementation. You can enable it, and we'll explain in Lab 20 how to do it. But in the baseline bit stream and the sources, this one is disabled. The catch is accessed. In case of a hit, the instructions are provided to the next stage. In case of a miss, the instructions are requested to the external memory through the memory controller. A 128-bit bundle is fetched every 2 cycles. So note that these are 32-bit instructions. So 128 bits is space enough for 4 instructions, unless they are compressed. RISC-V includes, and this processor supports the compressed extension, which has 16-bit instructions. But for normal instructions, we have 4 instructions per 2 cycles, which is enough for feeding the processor with 2 instructions per cycle, right? So this 128 bundle is buffered in these 3 buffers, and in the align stage, 2 instructions, 2 32-bit instructions are selected and assigned to each of the 2 ways for being executed in the next stages. So after once this align stage finishes, we have in the instructions registers 2 instructions ready for decoding and execution. Note that these are the names for the real signals that you will find in the core. So in case you want to understand how the iCatch is implemented or whatever, you have, well, these are the real signal names for the inputs and outputs for the iCatch. Next, the decode stage decodes the instruction, generating the control signals, which are propagated to the next stages, and also the register file is accessed. The register file in this processor has 4 read ports and 3 write ports. Here we only show 2 of them, because the third one is for a specific case that we analyze in a later lab. We'll see later. So we have 4 read ports because we need 4 operands per cycle, because we have 2 instructions executing. And we need 2 write ports because we may have to write back 2 results in the same cycle, right? The decode stage also assigns the 2 instructions to the proper pipe. So we have 2 integer pipes, I0 and I1, which include an arithmetic logic unit, 1 each. We have a multiply pipe, which includes a 3-cycle multiplier. This is pipelined in 3 cycles, in 3 stages. And it has the ls pipe, which allows us to execute load and store instructions. After the 3rd execution stage, the result is selected and propagated through the commit stage to the write-back stage, which writes the result in the register file. Note that there is also a divider out of the pipeline, because it's not pipelined, it takes 34 cycles. So when a division is executed, the pipeline is stalled until the end of the division. Okay? We supplement this figure with a verilator simulation that I'm not showing here, but that you can find in the document for this lab, for lab 11. And you can even try to replicate, and you can add other signals to the ones set by default, whatever. We also explain in this lab how to access the hardware counters available in the processor. We have 51 events that we can measure, such as iCatch hits and misses, number of multiplications, divisions, loads and stores committed, branch predictions, branches committed and mispredicted, branches taken, and many others. We give a program where we configure the performance counters for measuring 4 of these events. The processor contains 4 hardware counters, so we can measure 4 events at the same time. And we give an example in order to show you how to configure the counters to work. We'll use the hardware counters in subsequent labs for, well, for measuring performance and other things. Well, this is a long lab, but for the workshop, that's enough. You can take a look at the document. So lab 12 explains arithmetic logic instructions, how they execute in SweRV EH1. And we base our explanations in an add instruction, but we can extend the analysis to any other arithmetic logic instruction following a similar procedure. Let me show you a summary of this lab. So we use this simple program. Not that it's an artificial program, it does nothing. We only wanted to analyze an add instruction. We include an add instruction in an infinite loop, and note that we usually surround the instruction that we want to analyze with a number of knobs. This is a macro that includes 10 knob instructions before and after the add, so that we can isolate one add, each add of the other iterations, okay? So that otherwise it may be difficult to analyze a single instruction. So we insert this artificially for being able to analyze better the instruction that we want. And this is the very later simulation that we obtained for that example. Let me explain the signals that we're including. You're going to replicate this in your computer now. But let me first explain what we can see here. So we have the PC, which is this number, 108. This is where the add instruction is mapped in memory. This is the instruction register. This is an add T3, T3, T4. Okay, in the workshop document, you can understand this. We include here some explanation about encoding instructions in RISC-V, so you can try to understand why this is this instruction. And then we have the register address, which is 28 and 29. Note that T3 and T4 are just aliases for registers 28 and 29. Okay, so what we see in the signal is 28 and 29, but this corresponds to T3 and T4. And these are the values that we read from the register file, 7 and 1. So in the next cycle, so this would be the decode stage, right? So in the next cycle, the first execution stage, we can see that the ALU is adding 7 plus 1, obtaining 8 as a result. And this value is propagated until the write-back stage, where the enable for writing in register 28 is this signal is enabled. So we will write into register 28 the value obtained from the other, which is 8 in this case. And in the next cycle, you can see that the value stored in that register has changed from 7 to 8. Okay? So this illustrates the execution of this instruction in the SweRV EH1 processor. And we also include this figure as a supplement to the simulation, where you can see that the decode stage decodes this instruction. It accesses the register file, reading registers 28 and 29, obtaining 7 and 1, which are added in the arithmetic logic unit, obtaining 8, which is written back to the register file in the last stage of the execution. Okay. We ask students to analyze other arithmetic logic instructions, such as these listed here, in a similar way to what we've done with the add instruction. And we also include some exercises which are taken from the basic textbooks from Patterson and Hennessy and Harris and Harris. These are exercises that are proposed for their proposed processor. Okay, they use a 5-stage pipeline processor, and they include some exercises analyzing different features of that processor. So we adapt those to the SweRV EH1. So this is simply an example. This exercise taken from Harris and Harris' book, and also Patterson Hennessy, apparently, where when silicon chips are fabricated, defects in material and manufacturing errors can result in defective circuits. A very common defect for one signal wire to get broken and always register a logical 0. This is often called a stack at 0 fault. So we've adapted this exercise to analyze the effect of control bits included in a signal from SweRV EH1 being stack at 0. So you have to analyze those signals and say what would it happen in our processor in case we had this fault. Okay? And similarly, well, other exercises are adapted to our case. Okay? Just a sample of the exercises included in this lab. So let's try to replicate the simulation of this instruction. You have the guidance in page 25. Remember that you have to generate the trace in Verilator for this program. So first you have to open this program in Platform.io, generate the trace, and then open it with GTK wave and try to find and analyze execution of the add instruction at any iteration. You can analyze any iteration.